Hello, good evening, everyone. We are going to start off with quantum physics. Okay, by sort of looking back dun sa lessons nyo sa Physics 104, where you were first introduced dun sa quantum physics and sa objects na nagbe-behave in a manner it can only be explained by quantum physics. Karamihan ng mga objects or yung mga quantum mechanical behavior are observed in objects that are or atomic or subatomic na sizes. But they're not only observed dun sa ganong klaseng objects, but you can also observe them, for example, in light. Okay, so photons can be described using quantum physics, and even subatomic particles, okay, na hindi natin cover dito, okay, sa course na ito, are also described by quantum physics. Okay, at least yung may component ng quantum physics sa mga subatomic particles. To describe a quantum mechanical behavior, we should know yung tawag dito, yung wave-like. We should understand na itong mga particles na ito behave in a wave-like manner as well as in a particle-like manner. Depende kung anong klaseng measurements yung ginagawa, kung paano tinitignan yung object na yan. Okay? But in general, most of the measurements are in sort of a wave, sort of yung wave nature nung mga tawag dito, mga particles na ito. Okay? It's weird because we talk about particles, but we also talking about yung wave behavior nila. Okay, so how do we describe itong mga particles na ito? So we should be able to describe them in terms of where they are, so yung kanilang position, and kung ano yung momentum nila. So in some sense, we have this quantum behavior, okay, wave-like behavior, okay, that in Physics 104, we described using a wave function. Okay, itong wave function na ito ay dependent sa position and time. But in another sense, we also would like to know kung nasan yung particle na ito at kung ano yung momentum niya at a particular time. Okay. Time is also a parameter. Well, time is a parameter. It's not a variable in the sense ng position tsaka momentum. Okay. And we'll sort of brush on to that idea a little bit later. But going back dun sa point na kailangan nating makita kung ano yung position at saka momentum is akin dun sa ginawa sa classical physics, classical mechanics, in order to predict kung ano yung mangyayari in the future sa isang particle. We need to be able to know kung nasan yung particle at this time at kung ano yung momentum niya, okay, at this particular time. Similarly, sa quantum physics, we have that kind of sort of need na if we want to determine kung ano yung mangyayari sa particle na yun in a quantum mechanical sense, we also need to know kung ano yung classical properties niya, like yung particle position and yung kanyang momentum. Okay. To start off, in describing quantum mechanical behavior, gusto natin gumamit ng isang function, okay, that will describe yung wave-like behavior niya. And nabanggit natin kanina na yung light behaves in a quantum mechanical sense. Okay, so electromagnetism, you used tawag dito, a plane wave function, okay, to describe yung behavior ng yung wave-like behavior ng light. Okay, so you treated in electromagnetism, you treated light as a wave. Okay, pero you can also observe yung kanyang particle-like behavior in certain circumstances. Okay, so oops, ba't ganito yung itsura nitong? Okay. Okay, so I now reverted sa PDF version kasi mukhang yung PowerPoint yung may problema. Anyway, so ang sinasabi ko kanina is in order to describe yung behavior ng particle. Oops. Okay, so I reverted dun sa PDF version ng presentation, imbis na yung PowerPoint. So, ang sinasabi ko kanina is, in order to describe yung wave-like behavior, okay, ng isang particle, we use a plane wave function tulad sa electromagnetism. Okay, and this function has this form. Okay, psi of RT is equal to A exponential I K dot R minus omega T. Okay, yung R yung position, yung time. Of course, we know A is the amplitude, which you can determine by normalization. K is the wave number, and omega is the frequency, angular frequency. Okay, kung titignan niyo mabuti yung wave function na ito, okay, complex, okay, yung wave function. Okay, in quantum physics, this is problematic. Okay, pero in electromagnetism, okay, all you have to do is to separate yung real at imaginary components. And then yung real component, okay, ay meron na kayong interpretation. Okay, yung interpretation na yun yung nangyayari sa physical na. So sa tunay na buhay. Diba? So you can ignore yung imaginary components, electromagnetism, and then use yung real component to make an interpretation, a physical interpretation, an observation. Okay, but in quantum physics, this is absolutely not the case. Okay, there's no physical interpretation for a complex wave function. Okay, so hindi nyo pwedeng gawin yung ginagawa nyo sa EM na i-separate nyo yung real and imaginary parts, and then you try to make sense or try to come up with a physical interpretation of yung real component and ignore the imaginary component. That's not going to do anything pagdating sa quantum physics. Okay. However, you can sort of parang get rid of or like cancel out yung imaginary components, okay, by multiplying itong wave function na ito, okay, with its complex conjugate. Okay. So if you multiply this wave function, okay, by its complex conjugate, okay, then you're essentially taking yung modulus squared. Mathematically, this is what is happening. Okay, but in EM, in electromagnetism, this corresponds to intensity. Okay, so you're measuring the intensity of light. Okay, if you do this operation. Okay, in quantum physics or quantum mechanics, okay, this corresponds to probability. Or more specifically, probability density. Okay, anong ibig sabihin ng probability density? Okay. So when we talk about probability density, okay, we're talking about yung probability na yung particle, okay, ay makikita nyo throughout space. Okay, but this is probability density. So this is actually probability per volume of space or per dimension of space. So regardless kung 3D or 1D, so it's per dimension. So to actually get yung probability, you have to multiply it by some infinitesimal spatial value. Okay, so this gives us ito expression ito is the probability density at if you multiply it by some spatial differential, then you get this is the probability density, then if you multiply it by some spatial differential, you get the probability. So if we plot that probability density against x, as we see here in figure 1.2, okay, the shape of the wave function can be this. Okay, and if you are looking for the probability, okay, that a particle or let's say an electron, okay, can be found in a region like itong region ito dx, okay, yan yung mathematically yung area under the curve na yun is the probability. Okay. So probability. Yan yung probability na makikita niyo yung particle within that region. Okay? So, you can, of course, integrate over all space from negative infinity to positive infinity, just like what is being done here. Okay? And if you integrate over all space, that means na there is a 100% chance makikita niyo yung particle. Okay, anywhere in space. Okay. That's why when you do this integration, okay, yung integral na yan is equal to 1. Okay, because ang ibig sabihin nito is there is the particle is indeed in space or can be found in space. Okay. Pero yung spatial region na pinag-uusapan na yun is from negative infinity to positive infinity. Okay? So hindi confined yung particle sa isang region, but it's found it can be found anywhere within this infinite space. Otherwise, anong sense kung walang particle, di ba? Dun sa infinite space na yan. Okay, and we use that normalization condition to actually determine kung ano yung wave function. Sorry, kung ano yung amplitude na ito. So this is obtained from normalization. Okay? Okay. So ano ba yung properties ng ano na to, ng mga wave functions na ito? Okay. Well, tulad ng sinabi natin kanina, we need to find yung position at saka yung momentum ng particle. And how do we do that? So we already know how to determine yung probability. Okay. But if we want to find yung position ng particle, okay, ang gagawin natin is to sort of provide, to weigh the probability function with a position R. So mathematically, ang ginagawa natin is ini-insert natin yung R, okay, dun sa integral. Okay, ini-insert natin yung R dun sa integral. So, yeah. So, if you want to find yung kung nasan yung particle at a particular time, we're actually looking at yung average position or yung expectation value of the position operator. Okay, so unti-unti na kayong i-introduce sa mga quantum mechanical terms, di ba? So, this will allow us, or this will give us information kung nasa na yung particle at a particular time. Similarly, yung momentum ng particle at a particular time can be obtained by tawag dito by adding or weighing the probability distribution with momentum P. Mathematically, this simply corresponds to P, okay, na nandiyo dyan, okay, yung momentum. And anong tawag dito? And then what you would get here in this case is the average value of the momentum or expectation value of the momentum operator. Okay, so when we say expectation value of a tawag dito of a property. Okay. So gamitin na natin itong term na to. I was trying to avoid using that term. In quantum physics, we have this term called observable. Ang examples niya ay R, P, okay, position, momentum. Okay, basically these are measurable quantities. Okay, and if you want to obtain yung expectation value of any observable, ang notation dyan is itong brackets na ito, itong ganitong klaseng type na bracket. Ito yung A, okay, and then yan yung close brackets, okay? So this is the expectation value of observable A. Okay? Yung A na yan, yung observable na yan are actually operators. Okay? Makikita nyo kung bakit sila operator mamaya. And when you talk about operators, you usually put a caret on top of the letters. So yung observable A, which is also an operator, okay, ay lalagyan din natin ng caret sa ibabaw ng kanyang symbol. Okay? Okay, so again, if this is the observable, it's a measurable quantity. In order to find its average tawag dito value, okay, you're actually solving for the expectation value of the observable, and yung notation for the expectation value of the observable is this. Okay, now I want you to notice something. Oops, bago yung kulay. Okay, anyway, I want you to notice something dito. Pansinin ninyo na yung average position, okay, is in terms of R. Okay, so psi R, psi R, psi R, okay, psi star R. On the other hand, yung expectation value of the momentum operator is in terms of this wave number, K. Okay, so this is an integral in real space. Okay, in the space na ginagalawan natin ngayon. This is a real space because we're using we're using the coordinate systems that we're familiar in. Cartesian coordinate system, diba, can be described by dr. Okay, tawag dito, spherical polar coordinate system can be described by dr, and so on and so forth. On the other hand, yung expectation value of the momentum, okay, is an integral in K space. Ano ba tong K na ito? Well, K is actually momentum. Okay, and it's related to momentum by means of this anong tawag dito? This parameter. Okay, or by means of this relation. So this is what we know as momentum, and this is also momentum in quantum mechanics. Okay, so this is momentum in real space, and this is momentum in K space. So ano ang ibig sabihin ng K space? Okay, now here's the thing. So I suppose sa 131, no? Pinag-aralan ninyo yung Fourier analysis or Fourier transform. Okay, gumamit kayo ng techniques na fast Fourier transform to convert an audio signal, okay, which is in the time domain, so yung x-axis niya ay time, to a frequency domain. Okay, so to do that, to convert a time domain signal to a frequency domain signal, okay, you use Fourier transform. So you're looking at a signal in time, and then once you do a Fourier transform, you're going to look at the signal in frequency domain, in the frequency domain. Anong na information na makukuha niyo sa frequency domain? So ang makukuha niyo dun is, of course, pag may mga peaks sa specific na points, then you say, okay, so itong signal na na-measure ko ay merong frequency na ganito yung value. Kung marami siyang peaks, okay, ibig sabihin yung signal na measure ko dun sa time domain, okay, ay merong ganitong mga frequencies. So you can actually take an audio signal, apply Fourier transform, and then determine kung ano yung mga dominant na frequencies dun sa signal. And then that's actually what you did in Physics 131 in one of the machine problems. So there is an equivalent, okay, with respect to space. Okay, if you have real space, okay, and you apply Fourier transform, you convert it into momentum space, into K space. Okay. How can we understand kung ano yung K space? Well, tawag dito, ang gagawin ko is actually to confuse you even more. Recall na sa time domain, ang relationship ng time domain sa frequency is that they're inverse of each other, di ba? So, if you recall, ang tawag dito, period of oscillation ng isang object is 2 pi is 1 over f. Okay, so oops, ang nangyari dito. Okay, release ko na lang. Okay, so yung period is 1 over f. Okay. So actually, yung period ay may units na second at yung frequency ay may unit na hertz, which is just equivalent to 1 over second. So you can think of yung frequency domain as the inverse of the time domain. Similarly, okay, yung real space, okay, pag kinuha niyo yung Fourier transform yan, you go into K-space. Okay? And once you go into K-space, ang interpretation yan is that it's the inverse of the real space. Okay? So, yun. So, medyo mas naging confusing. Ano? And the only confusion is that, paano mo kasi imaginein kung ano yung tawag dito, inverse space, di ba? Yung inverted na space. Well, hindi ko na i-discuss yung mathematics niyan. Okay? Ang kailangan nyo lang concern ngayon, at least for this meeting, is that if you perform an inverse Fourier transform of a function in K-space, then you go back to real space. Okay? Yung discussion about K-space and real space will be tawag dito, provided in more detail pagdating yung sa solid state physics, na kung saan yung solids, yung objects, okay, yung compounds, okay, tawag dito, or para ma-describe yung kanilang crystalline structure, they are more conveniently tawag dito, describe mathematically pag ginagamit niyo siya or pag ginagamit niyo siya in K space rather than in real space. Okay? So ang concern lang natin dito is yung real space, yung average position, okay, is defined in this manner in real space. And then yung average momentum, expectation value of the momentum operator is defined in K space. Okay. And to convert from real space to K space, you need to do Fourier transform. And to go back to real space from K space, you need to do an inverse Fourier transform. Okay, so yun ang i-try natin gawin dito. Okay, so what we're going to do now, okay, is to start working on this expectation value of the momentum operator. Okay, tapos, oops. Okay. Tapos, ang gagawin natin ay mayroon tayong i-derive na quantity, okay, na i-discuss natin after ma-derive natin. So let's start with this, okay, with this expression. So beginning with this expression, okay, in one dimension para mas madaling magtrabaho. So in one dimension, the expression above, okay, is reduced to this. So expectation value ng P sub x, okay, ay equal sa integral, okay, from negative infinity to infinity, negative infinity to infinity, okay, ng psi star, okay, k sub x, okay, and then t, okay, and k sub x din dito, and then yung p, which you define kanina as h bar k, okay, yun yung naka-insert dito, okay, h bar k. K sub x. Okay. Then, tinanggal din natin, kung papansin nyo, tinanggal din yung time component. Dito merong time component. Okay. Pero dito, tinanggal natin pansamantala yung time component, and that's easily done through the method of separation of variables. Okay. Nagagawin din natin mamaya konti. Okay. So, starting from that, okay, ang gagawin natin is we apply an inverse Fourier transform. So by applying an inverse Fourier transform, okay, we can end up with an expression, okay, that relates momentum to tawag dito, or that an expression for the momentum operator. Okay, so when we do a Fourier transform of psi of kx, okay, so ito yung psi of kx. Okay, so dito, applyan mo yan ng Fourier transform or inverse Fourier transform. Ito, applyan mo rin yan ng inverse Fourier transform. You end up with this. Okay. Okay, so in other words, psi of kx is equal to the integral from negative infinity to infinity of 1 over square root ng 2 pi. Okay, dx psi of x exponential negative I k sub x. Okay, so yan yung Fourier transform yan. Okay, so yung complex conjugate nito, okay, siyempre papalitan nyo lang tong negative ng positive sign. Okay, kaya dito positive yung sign niya, okay, at dito negative. Kasi dito, ito ay complex conjugate. Okay. Okay, let's see. Suburin ko lang yung ibang mga ano para hindi ganong confusing. Okay. Okay, and okay. So now that we have this expression, Okay, now that we have this expression, ang gagawin natin is we use integration by parts. Okay. Specifically, dun sa second term. Okay. So dito natin i-apply yung IBP, integration by parts. Okay, where UV, okay, ito yung definition ng integration by parts, and we let U be equal to psi x, so ito yung U, and then yung V prime is equal to exponential I, K sub x times x. Okay, when we do that, so ito na yung expression na ito, we end up with UV prime, UV, so 1 over negative ik sub x, exponential I, negative ik sub x psi sub x, evaluated from negative infinity to infinity. Okay. Plus integral integral ng u prime v dx. So ang u prime is this one, okay, and yung v dx ay ito at saka, yeah, and then may dx ka lang. Okay, so yun yung nakuha natin from doing integration by parts. Ngayon, anong gagawin natin dito ngayon? So, evaluate na natin siya, di ba? And how do we evaluate itong functions na ito, itong parameters na ito? Okay. So, syempre, kailangan natin malaman kung ano yung nature ng exponential na function. Okay? Hindi natin alam kung ano ang psi of x, di ba? So, ano ba ang exponential na function? Ang imaginary. Okay, so exponential I x. If you recall, this is cosine x plus I sine x. Okay. Plus or minus, so you see plus or minus. Yeah. Okay, so this function is actually oscillatory. Okay? Okay, now specifically, yung dahil meron kang negative sign dyan, hindi lang siya nag-oscillate, but it also decreases. Okay, as it goes towards in positive infinity and towards negative infinity. So in both directions, okay, nagiging zero, okay, yung exponential na yan. Okay, which means na itong square brackets na yan ay zero. Okay? So, again, marami kayong ma-encounter na ganito sa quantum physics. It's important na maintindihan nyo yung behavior ng mga functions. Okay? Okay. So, if that's zero, then we are left with this integral. At yung integral na yan na yung pinasok dito. So, yan yung makikita nyo dyan. Okay? Okay. Now, there's one more trick that we will be using here, and that is we are going to use this expression 1 over 2 pi. Okay, dito ko lang sa baba ilalagay. So 1 over 2 pi, the integral from negative infinity to infinity ng dkx exponential negative I k sub x, x minus x naught, x minus x prime. Shoot. X prime equal sa Kronecker delta ng x minus x prime. Okay, so, ano ba ito? This is actually the Fourier transform of the Kronecker delta. Okay, so this is also a Fourier transform nitong function na ito. Okay, saan natin makikita yan ngayon dito? Makikita natin yan sa dkx, okay, integral ng dkx, exponential ng negative ikx, and then yung x, itong dalawa, okay, yan yung magpo-form ng x minus x prime. Okay, so palitan ko ng kulay ng konti. So Yan, ito, at saka yan. Okay, yan yung integral na yan. Then meron ka pang 2 pi of course dyan. Okay, that will result to delta x minus x prime. Okay, dito pala, sinunod ko pala. So, what we'll end up with is, okay, so bali ito, ni-reduce siya dyan. No? So, yan yan. Okay, then you have yung dx dyan, and then yung 2 pi sinama na dito. Okay. So, when we use this, okay, we'll end up with yung dalawang natitirang integral in terms over dx at saka dx prime. Then yung psi star x prime. Then yung derivative with respect to x ng psi. Okay. Tapos yung negative IH bar na natira dyan. And then yung result na dx minus x prime ulit dito. But this is a Dirac notation, di ba? And this will only have a positive value if x is equal to x prime. 1 if x is equal to x prime and 0 otherwise. So, ibig sabihin, ito at saka to, dapat equal sila. Ito at saka yan, dapat pareho sila. Okay? Para mag-exist. Everywhere else, na kung saan yung x ay hindi equal sa x prime will be 0. So, what we'll end up with just a single integral over dx. Okay, then yung psi star x prime magiging psi star x na lang. Then you have yung partial derivative with respect to x ng psi x. Okay, so you end up with this. Okay. Now, we compare this final expression with this expression. Okay, and ano ang makukuha natin dyan? So, makukuha natin is yung P, okay, yung P dito is H bar K. Dito, yung P is negative IH bar, okay, D dx. Okay? So, in K-space, ito yung expression natin ng tawag dito, expectation value ng momentum. In real space, ito yung expression natin ng expectation value ng momentum. And in real space, we end up with this expression, negative IH bar partial respect to x. So in real space, yung momentum operator has this form. Okay? And now you can see kung bakit siya operator kasi it's a derivative operator. It takes the partial derivative with respect to x of anything that you put in front of it. Okay? In real space, yung position operator is just a position operator. Excuse. In momentum space, yung momentum operator is just equal to h bar k sub x. Okay, it doesn't do much. Pero in momentum space, yung tawag dito, spatial operator, position operator is equal to negative IH bar, partial with respect to P sub x. Okay. Now, this we derived just now. Ito can be derived if you start with this expression. Okay. And then you apply Fourier transform. Okay. And you'll end up with something like this. Okay. Pero in K-space. And then you compare it with your expression in real space. So you end up with this expression. Okay. Another way to derive the momentum operator is by using this expression. And this is actually exercise, let's see, or problem. Exercise 2.8. okay, which you can try to do. Meron din siyang solution, okay, but try to do it first, okay, if you like, and para ma-practice kayo. And then tignan nyo kung ano kung gaano ka similar yung solution ninyo dun sa solution na pinrovide nung dun sa book. Okay? Okay, so ano ang ano natin dito ngayon? So we have these expressions. Okay, for the momentum operator in real space, position operator in real space, and the momentum and position operator in K space. Okay. Now, these are tawag dito, basic or fundamental operators, okay, that you use in quantum physics paulit-ulit. Okay. So it's very common to use these expressions. Of course, most of the calculations ginagawa naman natin in real space. So yung position operator doesn't do much in terms of operation. Pero yung momentum operator takes the derivative of the wave function. Okay? So we now have itong mga operators na ito. So we just discussed yung position operator and yung momentum operator. Okay, and yung potential, okay, well, it can be considered as an operator, but basically wala naman siyang ginagawa. Okay, yung energy is considered as an operator, and ito yung form niya. Okay, IH bar, ang tawag dito, partial with respect to T. So, makikita naman natin yan dun sa Schrodinger equation. Okay, so in general, your expression for the average value or expectation value of any operator A, okay, can be written in this form. Na kung saan yung operator A, okay, is a function of x, of the operators x and momentum operators. Okay, now mapapansin nyo rin na yung position at saka momentum operator, they're sort of like, so itong position, yung position operator, it's tawag dito, it actually takes the derivative, sorry, yung momentum operator actually takes the derivative of with respect to position. On the other hand, in K space, yung position operator actually takes the derivative of with respect to momentum, okay, in momentum space. So mapapansin nyo parang merong sort of tawag dito, relationship between X and P. They're actually conjugate pairs. Okay, we call them conjugate pairs. Okay, and you know about these conjugate pairs from Physics 104 kasi these pairs are interrelated sa isa't isa kasi if you measure one, okay, then you also measure the other, but you don't measure both of them with equal certainties at the same measurement. Diba? Ang tawag natin dun is uncertainty principle. So if we tawag dito, if we know for certain kung nasan yung position ng particle, hindi natin alam kung ano yung momentum niya. Okay, and if we know for certain kung ano yung momentum, hindi natin alam kung nasan yung particle. Okay, and classically, in the classical sense, if you think classically, then this is problematic kasi di ba gusto nga natin alam yung X and P in order to predict kung ano yung nangyayari. Another conjugate pair is energy and time. Okay, so you can see na yung energy dito, okay, is tawag dito, yung energy operator is actually ang tawag dito, operating on a function, okay, by taking the derivative with respect to time of that function. Okay. Okay. So, at this point, alam na natin, okay, how to describe a particle. Okay, we know how to describe a particle using its wave function, but the wave function itself doesn't really tell us anything. So we have to get yung tawag dito, yung modulus squared ng wave function in order to determine its probability density. Okay, the probability density is the probability where you can find the particle. Okay, over some space. Okay, then to determine kung ano yung position tsaka momentum, include natin yung position inside the probability density as sort of a weighing function, as a weighing parameter. And ganun din sa momentum. Include natin yung momentum operator in terms of dun sa probability expectation value. Okay, expression for expectation value. Okay, and then ngayon alam na natin na yung momentum, or alam na natin how momentum and position act as operators both in k-space and in real space. So, ano nang next step dito? Well, of course, gusto natin ng isang compact na equation, okay, where we can use and apply to different physical systems, okay? And of course, dinerive nyo to sa ano, well, actually hindi nyo yata dinerive to sa Physics 104. But to derive this, we start with H. We start with classical knowledge of classical physics. Okay. One of the most commonly used methods is yung Hamiltonian. Hamiltonian is basically yung sum ng kinetic at saka ng potential energy. Okay, and the kinetic energy is basically yung momentum squared divided by 2m plus yung potential. Okay, so we know, okay, now if we consider H as an operator, okay, then this is an operator. And we know na yung P, yung momentum, is an operator, which is negative IH bar, partial with respect to X. Okay, so if we insert that there, okay, we'll end up with, and allow, by the way, we allow this to operate on a wave function, psi xt. So let's say H operating on psi xt will give us, okay, so P squared, so this will be P times P star, so negative, okay, and then H bar squared over 2m, okay, and then partial with respect to X, okay, second derivative, ng wave function na psi of xt, okay, plus V, and lagyan na rin natin ng dependence yung V para ma-generalize. So, operating on psi of xt. Okay. So, yan na yung ating expression, okay, which we call the Schrodinger equation. So this is in one dimension. Of course, in 3 dimensions, we can generalize this to 3 dimensions. Basically, papalitan lang natin yung R, yung X ng R. So partial with respect to, oh, sorry. Del squared psi of RT plus V of RT psi of RT. Okay. So ito na yung ating Schrodinger equation. Specifically, time-dependent Schrodinger equation. Okay, alam naman natin kung ano yan, ano? So that's just the derivative of the wave function with respect to x, y, and z. Okay. Okay. Now we can replace h operating on psi, okay, with the energy operator. Diba? Kasi basically, h operating on psi will give us yung energy on. So this will become the energy, and yung energy kanina is IH bar ddt. Okay, so yung left-hand side becomes IH bar partial with respect to t ng psi of RT equal na yun sa h, negative h bar squared over 2m del squared ng psi of RT plus V of RT psi of R. Okay, so tawag dito. So this becomes actually our Hamiltonian. This is our Hamiltonian by definition. Okay, so we write yung Hamiltonian operating of psi of RT is just equal to negative h bar squared over 2m del squared plus v of RT. Yan yung Hamiltonian operating on psi of RT. Okay, equal sa I h bar partial respect to t ng psi of R. Okay. So this is the time-dependent Schrodinger equation. Okay. So this is the time-dependent Schrodinger equation. If we now use separation of variables, okay, in one dimension na muna, okay, then we end up with this. Okay, we separate yung spatial component from the time component. Okay, so ang gagawin nyo lang yan is substitute nyo lang yan naman yan dyan. Okay. Okay, so we have negative h bar squared over 2m. Okay. In one dimension, this becomes psi x phi of t, okay, plus v of x psi x phi of t is equal to IH bar partial with respect to t and phi of x, psi of x phi of t. Okay, of course, this operates on this, so ito ay can be treated as a constant. Pwede siyang ilabas. And this operates on that, at ito ay pwedeng ilabas, can be treated as a constant. Okay, so gagawin natin is we divide everything by 1 over psi of xt phi over t. So matitira dito is negative h bar squared over 2m. Okay. So nasa labas na tong phi of t, di ba? And then dinivide mo by phi of t to. So makakancel ay makakancel na patitira is 1 over psi of x partial squared partial x squared psi of x plus, and then itong dalawa magka-cancel with this. Okay, v of x is equal to, tapos sa left hand side we have I h bar psi of x, okay, partial respect to t ng phi of t. Okay, divide mo ba yung ano yan, psi tawag dito, psi of x phi of t, this becomes 1 over phi of t. Okay, and ang ginagawa natin is we assign this to some constant. Okay, we say na, sabihin na natin yung constant na yun is energy. So this becomes then negative h bar squared over 2m, 1 over psi x partial with respect to x squared ng psi x plus bx equals to e, multiply everything by psi x. Dito ko na ilalagay. So negative h bar squared over 2m partial with respect to x. And psi x plus bx psi of x equal to e psi of x. So yan yung Schrodinger equation na time independent. Time independent Schrodinger equation. Okay, what about this one? So dito, magiging partial with respect to t. So IH bar phi of t is equal to E phi of t. Okay, so this is a first order differential equation. Okay, now solution I. Phi of t is equal to exponential negative I omega t, kung saan yung omega is E over H bar, or E is equal to H bar omega. Okay, so E over H bar. Okay. So, yan na ito. Ito na yung time independent Schrodinger equation at ito na yung solution doon sa time component. Okay. So, okay, so yung Schrodinger equation na time independent. Okay. So now we can work with that equation. So we know that the wave function is psi of x. Okay, as time independent case, di ba, pag time dependent siya, or pag may time dependent siya, basically, due to the separation of variables, you can simply write I omega t, di ba? Ito yung psi of x, ito yung phi of t. Okay, dahil sa separation of variables yan. And if you take the complex conjugate of that, then you end up with complex conjugate of psi of x, and then ito exponential negative I omega t and exponential positive I omega t. So this cancels out, and you'll end up with psi of x, which is itong expression na ito. Okay. Now, yung normalization condition, okay, in one dimension, this is okay, in one dimension, this is a psi of so this becomes actually psi of r squared d3r, okay, equal to 1. So nawala na yung time dependence, okay, if you use yung separation of variables na technique. Okay, and in one dimension, it is reduced to this. Ito yung modulus squared mo, and then yung dx. And then they're not necessarily, yung subscript dito, yung n at saka m, they're not necessarily the same. Okay, to generalize, ginamit natin to expression na ito, which uses itong Kronecker delta na ito. Alam natin na yung Kronecker delta is equal to 1 if n is equal to m, and 0 if n is not equal to. And yung meaning ng subscripts na yan, okay, will be, tawag dito, will be described later on. Okay, although alam niyo naman siguro yung meaning yan kasi din sa 101, basically yan lang yung tawag dito, yung states, di ba? Energy states. So for yung ground state, first excited state, and so on and so forth. Okay. Okay. Now, here is a short exercise. Okay. Now, if the wave function is normalized, in other words, if this is true, okay, then it remains normalized for all time. And that's what you're supposed to do dito sa ano na to, sa exercise na ito. And ibig sabihin nito is that at t equals 0, normalize yung wave function mo. And at the next time, normalize pa rin siya. And for all time, normalize pa rin yung wave function mo. And of course, gusto nyo na ganyan yung case. Kasi ano bang ibig sabihin ng normalization? Normalization means yung probability na makita mo yung particle over all space, over infinite space is 1. The particle is there. Hindi lang natin alam kung saan exactly because it's in infinite space. And as time progresses, okay, andyan pa rin yung particle. It may move around. It may have stayed in one position. We don't know. But at least alam natin in infinite space, nandyan pa rin yung particle. So that it remains normalized for all time. Mathematically, that can be proven. And to do that, so you take the derivative with respect to time nung probability. And you show that that derivative is equal to 0. Okay, so this will be the derivation. Okay. Let's give it +2 bonus points sa exam. Okay, and you'll find a VLE link kung saan nyo isasubmit yung derivation na ito. Okay, dun sa tawag dito. Well, dun sa VLE. Okay, so just write your derivation on a piece of paper. I'll give you until next meeting to make a submission, okay, before 6 p.m. Okay, and yeah, so isulat nyo lang yung derivation nyo dun sa isang papel and you submit it, upload it dun sa VLE. Okay. Siyempre, meron na tayo nung Schrodinger equation. Now, the Schrodinger equation is very similar to, you can compare the Schrodinger equation to Newton's laws of motion. So if classical physics has Newton's laws of motion, quantum physics has Schrodinger's equation. Okay, so you start off all your calculations from Schrodinger's equation. Okay, let's apply this now to a free electron. Pag sinabing free electron, anong ibig sabihin nito? Ang ibig sabihin is that hindi siya nakakaramdam ng potential. Okay, so it doesn't feel any other energy that is tawag dito, that is exerting a force on an electron. Contrary to halimbawa yung electron orbiting in space, orbiting around a nucleus, di ba? Yung potential between that electron and the proton or the nucleus, okay, is given by yung charge squared divided by R, diba? Times yung constant na K. Okay, so merong potential siya naramdaman and the reason it's going around because yung force of attraction between the electron and the proton is present. Okay? Pero if there's no potential, if there's no force, then yung electron na yun will move out of orbit and just float around in space. So when we say it's a free electron, what we mean is that the potential is 0. So if we apply Schrodinger's equation here, mapapansin nyo na wala yung potential term. Okay? Kasi 0 nga siya. Equal na siya agad sa E sub n psi sub n x. Okay. Okay, so yung energy eigenvalues, okay, and energy eigenstates. Okay, so we call, so now we introduce a new term, no? We have these eigenstates and then we have these eigenvalues. Basically, eigenstates are these wave functions that describe yung tawag dito yung behavior ng electron at a particular state. And then yung eigenvalues ay yung kanyang energy at a particular state. Okay, and in the case of the free electron, okay, when you um, uh, when you tawag dito, try to solve this equation, okay, so dapat yata merong partial square dito. Yan. Okay, when you try to solve that equation, then you'll end up with this solution. You can check if this is the solution by plugging it there. Okay, and tignan nyo kung tama yung solution. Okay, and yung eigenvalues, okay, are also given by this. Okay, pag pinlog in yan dyan, ito dapat yung lalabas na eigenvalues. Okay, so ano ang description natin dito ngayon? Okay, so ang ibig sabihin nito is that um, when you apply or when you operate on this wave function, you get this. When you operate on this eigenstate, you get this eigenvalue. Okay, so ganun parati yun ano, sa quantum physics. If you have an Hamiltonian operating on a wave function, you'll end up with its corresponding eigenvalue. Okay, so an Hamiltonian operating on an eigenstate will give you its corresponding na eigenvalue. So there's a theorem for that na i-discuss natin in future classes. Okay. Okay, to solve for yung momentum, di ba sabi natin, kailangan natin malaman kung ano yung position niya at ano yung momentum niya in order to describe yung particle. So to solve for the momentum, we simply apply yung momentum operator dun sa wave function. Okay, so this is the momentum operator applied on the wave function. And then, ito yung tawag dito, ito yung lalabas dyan. Kasi ito yung ating wave function. If you take the first derivative, ito yung lalabas. And then, of course, if you add in yung time component, then ito yung yung may include dyan. So phi of t. Okay. Well, actually, it doesn't matter kung nandiyan yung time component or not. Dito sa calculations lang ito. Okay, you'll still end up with this expression. So, yung momentum operator is actually p h bar k kx okay, along the x axis. Okay, so now we have this. We know yung momentum niya, okay, and we also know yung energy. Okay, now we can one way to describe yung behavior ng particle is in terms of what's a graph called a dispersion relation. Basically, dispersion relation is a graph of the frequency as a function of the wave function of or the wave vector. So makukuha niyo yung function na yun dito. Okay, sa case na ito ng free electron, diyan yung makukuha yan. So syempre magka-cancel yung h dyan, di ba? Ang matitira dyan is omega k is equal to h bar k squared over 2m. Okay, and if you graph omega with respect to k squared, it's just a parabola. So ito yung parabolic function, okay, which we obtain from this. Okay. So yan, ang tawag dyan is a dispersion relation. And in materials physics, materials science, yan ang hinahanap or yan ang tinatry pa natin na isolve ng mga scientists. Kung ano yung dispersion relation. If you apply a potential, you'll have a dispersion relation which is probably has this shape. Okay, depende kung ano yung potential na yon. So magkakaroon ka ng sort of gap dito. So even though this is frequency, no? If you multiply this by frequency siya, if you multiply this by h bar, then it becomes energy. So this is an energy gap, okay, which you call a band gap, okay, an energy band gap, okay, na kung saan walang hindi present yung yung electron. Okay, so in in systems na mayroong potential, that could come out. Okay? And sometimes, dito pa nga lumilitaw. Okay? So, nandito shifted. Okay? So, may shift yung lowest point ng gap, okay, in some systems. And it can even be more complicated than that. Ang point ko lang dito is dispersion relation is a very important graph that will allow you to describe yung behavior, okay, no ng isang material. Okay, and we start learning about dispersion relations, okay, from the free electron, the concept of the free electron. Okay, so now we take a closer look at where the electron is. Okay, and in measuring where the electron is, ang ginagawa natin actually is we create a Gaussian pulse, okay, at the initial time t equals 0. Ano bang itsura ng Gaussian function? Itsura ng Gaussian function is this. Yan. So yun yung ito yung position ng tawag dito nung most probable position nung tawag dito nung particle. And ito naman yung delta x is yung spread, okay? Or uncertainty. Okay? So ganito yung itsura nung Gaussian function. So t equals 0, ganyan itsura nun. Yung peak and is at x naught. And then from the top to the bottom, kunin niyo yung kalahati niyan. Okay, kalahati. Then you measure itong width na ito. Okay, yung width na yan yung delta x. Okay, so ang tawag natin sa width na to is full width at half maximum. So yung full width at half maximum, yan yung delta x. Or yung tawag natin na uncertainty in position. Okay, yung amplitude ng wave function is given by this 1 over 2 pi delta x squared, fourth root. And then yung mean niya, yung most probable position niya is at x naught. And then yung delta x is the spread of the wave function. So yung probability density at t equals 0, okay, is given by yung wave function times its complex conjugate or modulus squared. Of course, ang mawawala dito ay itong complex term. Ang matitira lang ay yung Gaussian function, okay, which is written as this. Okay, and how do we determine kung nasan yung tawag dito electron? Well, we also need to know kung ano yung kanyang momentum. Okay, and we write yung momentum niya in terms of a Gaussian din, wave function. Yung momentum na wave function in terms of the Gaussian wave function. So again, this is also Gaussian. Okay, tawag dito. So yung momentum is written as this. Okay, so ito yung Gaussian component. And kung papansin nyo, delta x yung nakasulat dyan. So what we have now is delta x or delta k is equal to 1 over 2 delta x. Kasi dapat yung Gaussian yan is k minus k naught squared over 2 delta k squared. Okay, parang dito. Okay. 4 over delta x squared. Sorry, 4 dapat ito. 4 delta x squared. So if you compare 4 delta x squared with this one, then you end up with this one. And yung probability density is given by this. Okay, mawawala itong part na ito. Yung mean value niya is given by that. Okay, and yung spread ng wave function is given by this and is related to delta x through this equation. So now we have this relation, okay? And if you multiply this by h bar, okay, you get h bar times delta k. H bar delta k is nothing but delta p, yung momentum. So kaya merong delta p dyan. Delta x is equal to h bar over 2, which is yung Heisenberg's uncertainty principle. Okay, now, to determine kung nasan yung electron in the future, okay, ang gagawin natin is, from the expression for the momentum of the wave function in k-space, okay, ang gagawin natin is you're going to expand this part using a Taylor expansion, okay, and then apply a Fourier transform. Okay. So what will end up is this. Okay. Ang pinaka-importanting part dyan is this one. Kasi now, this has a time dependence. Okay, kung titignan nyo dyan, merong t, and then merong t. So delta x is dependent on time. Ito yung time dependence niya. At makikita natin na if we graph this, then we have, at any time t in the future, we have this wave function. So ito yung bago niyang x naught, okay, and then ito yung bago niyang uncertainty. Okay, so for the width of the wave packet to double, ito yung characteristic to time. So in other words, ito yung time it takes kung saan yung width doubles from this, okay, to this. So nag-double. So if this is delta x, then this is 2 delta x. And that corresponds to this. Okay, so I know that I've skipped a lot of steps kung din-describe natin ito. Okay, but it's fine kasi it's something that you can read dun sa book. At this time, okay, yung steps na yun ay tawag dito purely mathematical, but yung mathematical treatment na yan ay well, magagamit pa rin naman natin sa course na ito, but we'll be using some other mathematical treatment, okay, in this course, okay, para mas na mas convenient at saka na mas convenient, okay. So ang gusto ko lang palabasin dito sa ano na to, sa araw na ito is that we have or we derived, okay, yung unang-una yung wave function that can describe yung quantum mechanical behavior ng isang particle. Using that wave function, we know how to get yung probability, okay, probability density ng isang particle. Okay, we know how to get yung kung position niya, tsaka yung momentum niya. And then we were eventually able to sort of derive yung Schrodinger equation. And we applied yung Schrodinger equation dito tawag dito, sa isang system na walang potential. Okay? So yun yung takeaway ninyo para sa araw na ito. Okay? Now, if you have questions, just tawag dito, take a screenshot of the slide kung saan meron kayong tanong. If you have questions about the steps, okay, dun sa mathematical procedure, refer muna kayo dun sa book. And then, kung meron kayong steps sa book na hindi nyo naintindihan, then saka kayo lumapit for consultation. Okay? Merong exercise akong iniwan sa inyo, which results to bonus points sa exam. And you can submit those exercises. The deadline is on Thursday, August 29, 6 p.m. Okay, before the next class. Sorry, Friday. Okay, Friday, August 30. Okay, 6 p.m. Okay. So, thank you for coming, and I hope na meron kayong na-pick up for today.